All right, everybody. We're going to do a mechanism for beta decarboxylation. Beta decarboxylation. If you have a carboxylic acid that is beta to another carbonyl, here is the carbonyl. This is a Ca, carboxylic acid. Carbonyl has an alpha position and a beta position. Okay? If you have that story where you have a carbonyl that is beta to a carboxylic acid, then this mechanism happens with only heat. That's what the triangle is, right? Heat. And the reason why this happens is this number of electrons going in a cycle is unusually stable. The flow of electrons itself is very stable. We're going to devote a whole chapter to the stability of electrons going around in a circle. It's called aromaticity if you're a molecule. In a mechanism, it's called a pericyclic reaction. Peri means around the outside. Cyclic means cycle. So a pericyclic mechanism right here. See the electrons going around in a circle? We love it. And it's not a hard mechanism. It's those three arrows. And then an enol intermediate. Enol. And you know what enols like to do. Big word. Starts with a T, ends with an N. Tautomerization. So that's the mechanism in a nutshell. We're going to get the carbonyl is now a C with an O bonded to an H. There's an ene here. And the other product, I hate to say it, we don't have to draw. No, I don't hate. I love to say it. We don't have to draw it. It's already there. That's CO2. This beta carbon is now the carbon in carbon dioxide. And there you go. You're almost there, enol. And then our famous tautomerization. Yes. The problem is, every tautomerization we've done, we've either used an acid catalyst or a base catalyst, and there's no other molecules present in this mechanism, so you can't use either. Oh, what do? You need a molecule that provides a proton for this pi, and you need another molecule to grab this H using its pi. No, it's its own acid-base catalyst. No, I'm looking for the word intermolecular. The pi grabs an H, but it can't reach it. We have a way of showing that. Pi grabs that H, but it can't reach it. How do you say it reaches it from another molecule instead? Intermole. I need that word, ladies and gentlemen. I need that word on the arrow where molecule A is grabbing an H from molecule B. And then the sigma becomes pi, and you be done. You like it? Make the arrow black here. Nice. We're done. And what do you get? You get CO2, that's decarboxylation. And you get an aldehyde in this case. So if I had to predict this product, because that's our next exercise over here, how would I do it? Well, what did you do to this structure to predict this product? We have a question first. Oh, shit, we have an answer first. Okay. Yes, sorry, Miss Bottle. Oh, sorry, I said your name. Is that okay? Okay, just this once or forever?
It's okay. It's forever.
Oh, forever, okay. Right.
Actually, you got rid of the carboxylic acid, right?
Yeah, and that's where that carbon went.
Yeah.
So you basically just circle this, get rid of it, and draw what's left. And remember, that H actually ends up on this C, so it's not a CH2 anymore, it's a CH3. And it's the same every time. Just grab the CO2 and get rid of it and zip the H back to the alpha position here. So I'm gonna do it over here. And I realize that the same scenario of a carbonyl having an alpha carbon here and then the carboxylic acid's beta means I can do this story, right? Don't worry, there's other places on this molecule where it's also going to happen. I'm just doing them one at a time. And that CO2H goes and the H ends up on the alpha carbon. So watch carefully what happens to that portion of the molecule. Ketone stays where it was. Oh, I should draw the ring the same orientation. This is all about learning. Let's not be rotating on the first time we see something. And that covers that CO2H on the left. It's gone. So I'm going to do some tickies here. I got rid of one CO2H over there. That's what that means. I'm going to add up all these tickies and put the number in here. And then over here, I'm going to do the same story. But remember, if there's a carbonyl beta to a carboxylic acid, this reaction works. Okay? Here's a carbonyl. Yes, it's a carbonyl that's in another carboxylic acid. Alpha is here, beta is a CO2H. You're going to get rid of it too. Got rid of that? Going to get rid of this? After you do that, there is no more carbonyl beta to this CO2H. Do not take off both of them. Does that make sense? I hope. You're only going to lose one of these. So here you are, CO2H. One of them remains. And down here, this carboxylic acid is not beta to any carbonyl. Alpha is here. Sorry, carbonyl is here. Alpha, beta. That's not a carboxylic acid. Alpha, and the beta carbon is not a carboxylic acid. Put an X on it. It's not happening, is what I'm saying. It's not. Nothing's happening there. If your carboxylic acid is not beta to another carbonyl, this reaction will not happen. End of story. That answers any potential question, I hope. That CO2H has to stay. That carbonyl never is going to go no matter what. There's my final answer. And I'm going to put it in the box. Oh, maybe not. Maybe I'm not so lucky, huh? Just redraw it. Got trouble. And carbonyl, ring size 5, carbonyl, still have this CO2H, not beta to any others, still have this CO2H. And I didn't do my 2 tickies and add them up to put a 2 here. Now it's confusing. It looks like an 11. There you go. 2 highlighted CO2Hs. We still might have a question? I don't know. Yes, Ms. Fowler.
I'm so confused about this one.
About which one?
How come we didn't get rid of it?
It's not beta, that carbonyl of that carboxylic acid, not like this one where the carbonyl itself was beta to the other carbonyl. The carbonyl of the carboxylic acid must be beta to another carbonyl. That's the only story. The carbonyl of the carboxylic acid must be beta to another carbonyl. This is not the carbonyl of the carboxylic acid. This is the beta position to this carbonyl. There will not be a decarboxylation here. And that's that. And we gotta call this one. There we go.